Summarize what we have learned so far. So we have discussed three types of problems. So the first category of problem is the unconstrained optimization problem. Unconstrained optimization problem is quite easy to formulate. So we always want to optimize the function, and we always want to minimize. So actually, it's the same as maximize, something. But in the formulation, we try to minimize the function. So we try to minimize scalar function in terms of vector control input. So this vector, all the control inputs are real. So we fully discuss the real input in the n-dimensional space. So these are the problem formulation. It's quite straightforward. Remember that I just want to remind you that the cost function itself is always scalar. The cost function is scalar, so it's easy to compare the cost function. So we can easily to tell the value is large or small. So that's the advantage of the scalar. So for the control input, it's a vector. So we typically define the control input to be a column vector. In this case, we got n inputs. So we define the control input to be a column vector with a dimension of 1. So these are the problem formulation. So the solution to the problem is we can evaluate two sets of conditions. So the first condition is the necessary condition. So the necessary condition is to evaluate the gradient to be 0. Evaluate the gradient to be 0. So in this representation, we know this gradient actually is given by a vector. It's given by a column vector. It's defined by this dj du1, dj du2 up to dj dun. So in this representation, all the components are scalar. So you know how to evaluate the equations. So this column vector needs to be 0. So all the components should be 0. So this will give us n equations. And there are n unknowns. So we can determine these n unknowns from these equations. So graphically, the necessary condition is to determine all the extremos. So for example, if we have a function like this, it's a j, here is a u1, say one-dimensional space. So the necessary condition will give us the solutions to all these extremos. So this is the first set of condition. The second condition is the sufficient condition. So the sufficient condition is given by this d square d u square is positive. the sufficient condition can distinguish whether these points, whether these solutions are minimizing solution or maximizing solution. So for example, there's the first one, there's the second one, there's the third one. So from the first set of equations, will give us these three solutions. And by evaluating the sufficient condition, we will know the second point is a minimizing point. And in general, this entity is a matrix. In general, this one is an n by n matrix. So for the n by n matrix, to tell a matrix to be positive, we need to evaluate the eigenvalues. So we have all the eigenvalues to be positive. So you can refer to the lecture notes to see how to evaluate this matrix to be a positive or not. So this is the first category of problems. So the second category of problems is the constraint optimization problem with equality constraint. So it's the equality constraint. Equality constraint problem. So the problem formulation is based on the unconstrained optimization problem. So the first part is the same. So we want to optimize a scalar cost function, also a scalar cost function, by using the control input, n-dimensional real control input of n. But in this time, the optimization is subject to a set of additional equations, subject to this equation, this f, the set of f equations to be 0. So we have this f, the totally f real equations. And for the problem to be well defined, we also require the number of control inputs is greater than the number of constraints. Otherwise, the set of constraints can already determine the control inputs if we have more functions than the unknowns are there. So this condition tells us in the constraints we have more unknowns than the number of equations. So these are the problem formulation. The first part is exactly the same, and we got additional constraint. So these constraints are some quality equations. So the solution to this problem is to construct the Hamiltonian. Construct Hamiltonian with the Lagrange multiplier. So the Hamiltonian is defined by the original scalar function plus a linear combination of the trains. So the linear combination is given by this Lagrange multiplier multiplied by the equations constraints. So by this definition, we know the Hamiltonian is also a scalar. This one is scalar because the J is the scalar, and this product is the scalar. So the first one is the dimension of 1 by m. The f is m by 1. So the product will give us 1 by 1 is a scalar. Then the necessary condition is given by this dh, du equal to 0, and dh, d lambda equal to 0. So the dH du is similar to the dJ du defined here. So we have n equations from here. So this one will give us n equations, and the dH d lambda is actually just give us this f. So we have f equations and here. So totally we got n plus m equations, and we have n plus m unknowns. So the n into inputs and the m logarithm multipliers. So for the n plus m equations and the n plus m unknowns, so we can determine the control input uniquely by evaluating the set of algebra equations. So the third category of problem is the inequality constraint problem. So in this problem, so also the first part is the same. So we want to optimize scalar cost function with a control input, a real control input. So in this problem, we generalize the constraints. So we generalize the constraints to be the inequality equations. So in this equation, we know already have smaller or equal to 0. Actually, we can also represent the greater or equal to 0. So if we got a function, you got an f is greater than 0, you just multiply by -1. So you will change the equation to this form, the standard form. So in this form, we also assume there are m constraints. But however, we don't require the n to be greater than m. We don't have the additional requirements. So the solution to this problem is we also construct the Hamiltonian with the logarithm multiplier. So we construct Hamiltonian the same, it's exactly the same as before. We define Hamiltonian to be the original cost function plus linear combination of the constraints. And we require this dH du to be 0. So this will give us the n equations regarding the input. But because now the f is inequality equation, so we cannot directly calculate the gradient in terms of lambda. In this case, we have two scenarios. So the first one is if the constraint, so here m constraints, if the s constraint is inactive, so if the s constraint is smaller than 0, that means this constraint is not active. This constraint is not active. It's not active, so the corresponding lambda is equal to 0 because it's not active. It is not using here. Not using here, so we should set the lambda to 0. So secondly, if the S constraint is active, is equal to 0, so that means this constraint is active. So in this case, the corresponding logarithm multiplier must be positive. So in the past weeks, we have used examples to illustrate how to use these techniques to solve the optimization problem. So our course is about the optimal path planning. So now the problem, now the question is how to use these optimization techniques to design an optimal path, to find an optimal path. So from this equation, you know the solution is typically a control vector. So you may think about this to be a point, but how to use the techniques to find a path rather than a point to minimize particular constructions. So for the path planning problem, so for the optimal path planning, so typically we have two techniques to apply the optimization techniques to the path planning problem. So the first category of techniques is the problem discretization. So we discretize the problem space. The problem discretization. So we try to discretize the problem space. So we get a set of control points. So we can optimize the paths in terms of the control points. So the second category of techniques is calculus of variation. So today we will discuss the first category of techniques, and later we will discuss the calculus of variation. So for the first category of techniques, so actually we already learned before. It's very straightforward to use. So the basic idea is like this. So assume we have a problem space. So for example, as in the first assignment, we got a starting point, and we have a destination right here, and assume there are obstacles in the space. So we have the coordinate system x and y, we have 0 and here. So in this space, we know there are multiple feasible paths. So by using the potential function method, we are always able to create a path. For example, we may generate a path like this. And if you change the parameters, maybe you will generate a path like this. So all these are feasible paths. But by using the potential function method, we are not able to optimize. We are not able to optimize the path. We know the optimal path probably is given by a path like this. So how to determine this optimal path? So the idea of the technique is to discretize the domain. discretized domain so that we can solve the optimal control problem at each point. So the idea is, so for example, we can discretize the space like this. So we have some control points in between. So all these are assumed to be the control points. So by using our techniques, we can optimize a particular cost function in terms of this control impulse. So this control impulse on these control points will eventually give us optimal path. So these are the general idea of the first category of technique, the problem discretization. So the problem discretization is a very powerful technique. So we may discretize the space by using different techniques. We may discrete the domain, the time domain, or in the spatial domain. So we have different techniques. So today we will discuss the technique to discretize the time domain, generate a path. And we use an example to illustrate the technique. So we use a simple example in the one-dimensional path planning problem. So in the one-dimensional path planning problem, we know our space it's a 1D space, and we got our mobile robot and here. So assume these are our mobile vehicle. So the mobile vehicle will move the one-dimensional space. So in the one-dimensional space, so it's only moving either in this direction or in the other direction. So we know in this space, we can easily define the coordinate system. So it's 1D space. So we only have one axis. So we only define this x, for example, the x-axis, and we also define a 0 point for the coordinate system. So for the path planning problem, the first step is to formulate the problem, or to define the simple dynamics of the vehicle. So as shown in our previous lecture, we know the simple dynamics in a one-dimensional space is given by this x dot equal to v. So the v dot equal to, I define this to be u. So the x is the location of your vehicle, and the v is the velocity. So in the potential function method, we have used the same simple dynamics. But in that problem, for two-dimensional space, so we have the x dot and the y dot. You still remember that, right? So in the 1D space, it's a reduced dynamic equation, very simple dynamic equation. But actually, for the path planning problem, we don't require the exact dynamics of your vehicle. So we typically assume the the vehicle to be a point. So we can use this simple dynamics. So the x is just the location of your vehicle. So eventually this x will give you the path. So actually these are the paths. It will give you the path of your vehicle. So the v is just the velocity. And we know this u will be the acceleration. So we know the acceleration is linked to the force applied to the vehicle. So we can treat this u to be the control input. So this u will be the control input to your vehicle. So these are the control input. So we can define the state space form. We can define the state space form for this equation. So you know, typically we define state vector. We define the state vector similar to your control cost. I think you have been quite familiar with the form. So we can define the state vector to be this x and the location of the velocity. So in this case, we have this x dot equal to this x dot, this v dot. We may get the matrix form for this one. So here are x and v plus another matrix multiplied with u. So it will be like a form like this. So the x dot is given by v. So these are 0, 1, and these are 0. So 0 multiplied by x, 1 plus by v, plus 0 multiplied by u. So that's all given by v. So the v dot equal to u. So these are 0, 0, and then we have 1 here. So in this form, we define the first matrix to be A, and this one is just the state vector x, and we define this to be matrix a vector of B. So we may have a state space form for the dynamics. It's x dot given by A x plus B u. So far it's nothing new. I think you already learned this, or you are already quite familiar with the dynamic equations in the state space. So next we want to discretize the equation. So we want to discretize the equation based on the derivative. So we know the derivative. The derivative is defined by for the x is b plus and b minus x b divided by the p. So we know the derivative. The derivative is given by this quantity, but with delta t, it's approach to zero. So we may approximate the derivative by this equation. So this is given by the equation here, given by this a xt plus b ut. So this step is very important. This step is very important to discretize the problem. So we may have this f, this x t plus delta t minus xt equal to a delta t xt plus b delta t ut. So this x t plus delta t equal to xt plus a delta t xt plus b delta t ut. So the x is defined by x and v, the state vector. So we may have this. We expand this equation into a matrix form by using this definition. So we have this x, the location at t plus delta t, and the velocity at t plus delta t. So this is given by the first vector. This is given by this xt is given by this x t way t. So in this equation, we can further combine the first two terms. We can combine this because both got xt. So this can be combined to be identity matrix plus a delta t xt plus b delta t ut. So in this equation, we know that a is given by 0, 1, 0, 0, and b is given by 0, 1, the column vector. So the identity matrix plus this a multiplied by delta t. So we got the first one is 1 plus 0, and the second one is 0 plus 1 multiplied by delta t. So we have delta t and there. So the third one, this component given by 0 plus 0, so we have 0, and the last one is the 1 plus 0 multiplied by delta t, so given by 1. Let's evaluate this quantity. So this matrix is given by this b multiplied by delta t. So the first one is 0, 0 multiplied by delta t, and the 1 multiplied by delta t. So in this case, we almost discretize the function. So we only got one parameter of delta t. So we know that delta t is a control parameter. It's a control parameter of the is a control parameter. So it can be defined by the user. So by using the subnotation, notation, the typically used the digital control. So we may have the x k plus 1, the v k plus 1 is equal to 1 delta t 0 1. So this xk, this vk plus this 0 delta t multiplied by uk. So now we have a discretized dynamic equation. So it's in a typical discrete format in terms of the k, and the delta t is just a constant. It's a design parameter chosen by the user. So far we just derived the dynamics of the vehicle. We have not dealt with the path planning. We have not defined the jack. So now we define the objective for our control. So assume our objective is to get the vehicle at t equal to 6 seconds at the location to be 1 and the velocity to be 0. So you may think about the problem like this. So at t equal to 0, so we have the vehicle at the location of x 0 equal to 0 and the velocity equal to 0. And we want to control the vehicle